I admire your pluck for having come to probably your last class before the break, right? Anybody got any classes after this? Did y'all survive your midterms? Yeah. Sort of? Yeah. All right. So, how many people were hoping for a snow day? Yeah. Anyway, so last time we were talking about the binary search algorithm. We had done it out on the chalkboard, and I thought a cool thing to do today would be to actually implement that in Python for the benefit of the viewing audience. So let's pull that together, shall we? So the binary search algorithm. Very briefly, let's recap how it works. You have a sorted list of numbers. You examine the middle element of that list of numbers. If that element is greater than the thing that you are looking for, you know you have to look in the lower half. If it's less than the thing you're looking for, then you know you have to look in the larger half. And once you know which half you're looking in, you constrict and constrain your search to that new half of the array, and then you repeat the same procedure. So let's do an. Okay, what do you want to see first? The iterative solution or the recursive solution?
Recursive.
Recursive. Awesome. I like the enthusiasm. So, def bin search. Taking a list L. So, first step in the algorithm is to identify. Yes? Can I erase the top line? Oh, right. Better? Awesome.
And could you also lower the lights in the front?
Yeah, I'll get the lights too. Yeah.
Different every time.
Ooh. So, so the first step in the binary search algorithm is find the halfway point. Thank you. So let's call it M for midpoint. L at length of L, integer divide by 2. It doesn't matter that it's not the exact middle, it's good enough. So, we then test this midpoint to see if it's greater than or less than the thing that we're searching for. And I suppose I should put the thing that we're searching for in there, eh? We'll call it E for element. If M is greater than E, elif M is less than E, else. So what's the else case here? Yeah?
Nailed it. It's easy. You got it right.
Yep, nailed it. Return. Let's return the index. So the index of M will be this guy right here. So we'll return that expression. Wonderful. So, if the midpoint is greater than the thing that we're looking for, what section do we look in? Left. Left corresponding to smaller numbers and lower indexes, right? So, we then invoke the recursive call in search. We'll use a slicing operation to section up the list in order to get the sublist. And we're, of course, going to continue searching for the same element, E. So, we want to go from the beginning of the list until what index?
Is it the one that you have, like L, like above that actually -1?
Yes. So remember that whatever you put in for the second index, the slice actually stops one before that index. But that's actually what we want in this case, because we want to exclude m from consideration because we've already tested it, right? So, actually in this case, it kind of makes a certain degree of sense to make this into a variable. Say, I is this, and then we can just, because I'm having to use copy-paste too much. If you use copy-paste more than twice, it means you should be using a variable. There we go. Is that all we need? Can anybody think of anything else that we might need for this case? Nope? Okay. All right, next one. Let's take a look. There we go. So this one, essentially, we want to do the same thing, but we want to take the other side, right? So we want to start the slice at I plus 1. Right? Because again, we want to exclude that middle value because we've already tested it. Does this make sense so far? Good. Awesome. So let's, this looks like it's complete, so let's test it out, shall we? So let's get a list, let's say list is equal to 10, 20, 30, 40, 45, 50, 50, 60, 70, 78, 80, 90, 100. There we go. A nice sorted list. Yes?
For the else statement at the bottom, do you still want to return L at I or just I?
So generally speaking, with sorting algorithms, in searching algorithms, there is one of two things that you'll want to return from the algorithm. Either you're looking for a simple Boolean test for presence or non-presence, right? Or you want to find the position at which this item might be found, rather than the item itself. We already know what if m is equal to e, we already know the value of m because it's equal to e, right? So we gain no information from returning that. So no, in this case, we're going to return the index at which the found element will be found. Does that make sense?
Yeah.
Cool. Good. So let's actually let's do one more. So we've done the iterative case here, but we're missing the base case. What's the base case? You answer a lot. Let me see if anybody else wants to. You, sir.
Like when we run out of things to check,
Right.
and then there's nothing else to check, so you return false.
Right. So what does it mean in this context, running out of things to check?
If the size of the list is 0.
Bingo. So we'll just slip that in at the beginning. If the length of L is equal to 0, return place. There we go. So, in search, list, somebody call out a number.
12.
Thank you. And Python read. There we go. Oh, we got an error. List index out of range. So what's the mistake that I've made? Yes, sir.
Is it because you define L and you call list?
Because I defined L and I called list.
Yeah, but you have L over there, list. Oh, never mind.
Yes, sir.
Is it that at the case where the list is empty, you like define I and then look for L of I, and L is an empty list, so it doesn't have an index that corresponds to I?
Yes, that's the answer. So, given, the element at index 0 is the first element. If the list is empty, it has no first element. So trying to access it will result in an index error. So, fortunately, this is quite easily solved. We just take this if statement, put it before this bit where we actually try to use that, and bing, bang, boom. Except it didn't actually print it because I didn't actually ask it to. All right. Grumble, grumble, grumble. False. All right. Somebody give me a number that's in the list. 40. Index 3. Perfect. Seems to work. So let's examine this a little bit in a little bit more depth. Let's take this and do some print statements. So print L. Actually, that probably would be sufficient. Yeah. So this is how execution goes when we're looking for 40. We start off with this big list. Well, you know what? Maybe I will identify what M is. Print M is equal to the value of M. There we go. Try again. There we go. So M is 50. We don't know which one, but it's this one. So we subdivide. We take this side, right? Then we get lucky, right? It just so happens that the item that we're looking for is this middle value, and then it works. So let's see how it works. However, if we're looking for 45. So the first two steps, it does the same thing. Then 40 is less than 45, so it takes this segment, boom, and then it considers this one. It's rounding up, so it thinks this is the middle, and then it takes the other side, and then it finds it. Make sense?
It's giving you like 0.
It's giving me 0. Oh, yeah, that's it. Oh, yes. Well, that would be the index relative to the list that we gave it, right? So that, I think, we can chalk that up to a problem with, that's not an easy problem to solve actually when we're doing things recursively, but it's easy enough to solve if we're doing an iterative solution, right? So maybe we would just want to say, in this case, we'll just return true if we find it. Because, you know, yeah. Question?
This might be a bit silly, but if you wanted to keep the original index, could you just have a separate argument
In theory, after that point, though, you're kind of still presented with the problem of how do you find the particular element that you're looking for, right? Because it's like, how do you get there? Do you use like a linear search inside of your binary search, you know? Are you invoking a second binary search within your binary search to find what the first one should have found, you know, that kind of thing? Question?
Well, the way that I did it, because I actually tried this already, and the way that I solved that was I have another like argument, but it defaults to 0. So if you, when you originally call the function, it has position 0, and then I change position every time based on the length of the thing.
Yep.
It's a lot of, it's like 20 lines, so it's more than that, but you know, it's similar.
Yeah, well, you know. Yeah, so what you're doing then is you're keeping track of an offset.
Yeah.
Yeah, absolutely, yeah. I don't think we're going to go there for this one, but yeah. So if you want to maintain the indexing, you can look for an offset, or you can maintain an offset through the argument. I'm sorry if I'm a little low energy today. I've literally been shoveling snow the entire day. I have a corner lot with a double wide driveway, and our next door neighbor is 93 years old, and she's got a driveway that's like kind of like a triple driveway, all continuous. So, and then I do her back porch because she's 90. It's just, yeah, she really appreciates it. She gave me $10 whole to do it. You know, it's just a lot of work. I'm really looking forward to winter not being winter anymore. But anyway, so let's do bin search 2. We'll do an iterative solution now, since we've seen the recursive one. So the difference between an iterative and a recursive solution to this problem, in the recursive solution, what we're doing is we're taking the list and we're slicing it up and passing that slice on to the recursive call. In this case, what we're going to be doing is we're going to be maintaining variables which keep track of the window of that list that we are interested in without actually performing any modifications of the list, right? So we start off, let's say we have A, which will be the beginning of our window. That will start off at element 0, assuming that the list is non-empty. So if you want to throw in a case for an empty list, come on, not block, and enter, thank you. You can, you know, if L is equal to an empty list, you can return false just off the face of it, because obviously, if the list is empty, it cannot possibly contain anything, including the thing you're looking for. So you can just return false. So A will be the beginning, B will be the length of the thing. Now, -1 because you don't want it to like exceed the size of the. You want L at B to give you the last element in the list that you're working on. So from there, we can copy these 2 lines because we still need to find the midpoint, right? But now we do this inside of a loop. So let's see. While A is not equal B. This might not be the most efficient solution, but it's what I'm capable of right now. So we have I, we have a midpoint determined. If M is less than E, do something. Else or L if m is less, or I said less than, but I meant greater than, and then else return true. So essentially, so you'll notice that the if structure on the interior here is very similar to that structure as it occurred in the recursive solution. In this case, however, what we're doing with this if conditional is we are updating the bounds of the valid region rather than using them to create a separate section of the valid region using slicing and then put that off to the recursive call. So, given that A is the lower bound and B is the upper bound, if M is greater than E, do we move the lower bound up or do we move the upper bound down? Yes. We move the upper bound down, right, because if the midpoint is greater than the middle element, then that must exist in the smaller half, right? So we can move, so we can say B is equal to M minus 1. Yeah? Conversely, if M is less than the thing we're looking for, we know that the thing we're looking for must be in the upper half of the remaining window. So we can move A up to the midpoint, and actually one past the midpoint. So A is equal to M plus 1. Good. So these two bounds will close and close and close and close and close until at some point they will become the same number. I just realized, however, that here is actually not the length of L anymore. What you want is the difference between A and B, right? So it's B minus A divided by 2. Because like, you know, if we have the list, and you know, A is here and B is over there, what we're actually interested in is the midpoint between A and B, which would be A plus B divided by 2. The average of the two, right? Make sense? Good. So, if we have made it to the point where A and B are the same, where A and B are the same number, we can just test that to see if it's the thing that we're looking for, assuming we haven't exited out on any other return statements so far. So we can actually just return L at A is equal to E, and that will return the correct answer. So, shall we try this thing out? Let's do it. Did I save it? Oh, I didn't.
Bin search 2, yeah.
Yeah, there we go. Thank you. List index out of range, line 54. Well, like if you want the average of A and B, then it's the sum of the two divided by the number. So that would be A plus B divided by 2, and that would get to the middle.
So you said minus 1.
Yeah. Let's see here. Well, when in doubt, this should be an informative exercise for everybody because I'm going to be debugging a program live on screen. So, First, let's print L. Each time this iterates, we'll just put a separator in. Print A is equal to A. Print B is equal to B. Print I is equal to I. We'll need to put that after. And one for M. So, okay, so okay, I know what the problem is. Can anybody else spot it? Yes. Speak up a little. I'm taking the value instead of the index here. So obviously, any one of these except the first one, if you used it as an index, would put you way outside the bounds of the array. So, yup, that'll do it. Boom. So there you go. And as you can see, it's sort of in a manner that y'all remember the x-intersect algorithm that we did in like the first day of class? Operates on a very similar principle, right? However, in this case, because it's discrete, we actually have a certain number of numbers that we have to go through. We're not like trying to find some increasingly precise floating point number, which is why we don't have to worry about epsilon. There's sort of like a built-in epsilon here, which is to say you want a number. Make sense? Any questions? Cool. All right, well, let's see how many of the slides I covered, shall we? So here's the binary search using recursion as given by the slides. As you can see, it's pretty much identical to what we were doing, but slightly better documented. Binary search using recursion is much faster because it only has to look at a small number of items in the list. If the list has a length of n, then binary search using recursion looks at approximately log base 2 n elements of the list. Well, this is not just true of recursion. This is not just true of the recursive solution. This is also true of the iterative solution that we did. The number of loops, the number of times that we loop through that loop is actually equal to the number of recursive calls that we would be making. And given that there is a certain degree of overhead involved whenever you call a recursive function, I would say if you timed the two of them, the iterative one probably ends up faster, and not by an inconsiderable margin. But yeah. So one piece of inefficiency, however, with the recursive solution that we were doing is sort of this issue of slicing, because if you all remember from when we were talking about immutable data structures and immutable operations, when we have an array, right, and we take a section of it, right, and we take a slice, we end up with a duplicate of it in memory, right? Now, when you take another slice, let's say this slice, right? You get another chunk of memory dedicated, take another slice, you get another chunk of memory dedicated, take another slice, you get another chunk of memory dedicated. You guys get the idea. It's actually kind of interesting, kind of after the manner of Zeno's paradox, the amount of memory that it requires the amount of memory that all these slices occupy is actually limited to the size of the original array. So to some degree, the binary search algorithm that uses slicing is paying for more memory than it actually needs. The version that uses indexing, which is given here, and also the one that we had that bug in, this version of the binary search algorithm does not require doesn't require the extra memory to store a bunch of extra array elements. All you need is the two additional variables in addition to the data structure that you originally had. So yeah, more memory efficient, possibly more efficient in general, actually. And that's not to say that recursion isn't good or isn't more efficient in some cases, but if it's something easy enough like this, then you don't recursion can be overkill, right? Recursion can be overkill? Yeah. So, anyway. Any questions about that? Good. So one other thing to note about this particular example, this is an example in the actual slides of a function within a function being used as a helper function. So search3 helper is local to search3. It does not exist outside of that context in the same manner as a local variable. Cool? We already talked about it. So we just have a couple more points to knock off with respect to functions, and then we'll be on to our next topic. So, in Python, functions are they are first-class objects. So Python is an object-oriented language. Everything in Python is an object, including functions. We can use functions like objects of other types. So functions may become the arguments to functions. This should be right? It's there's a fairly typical example of why you might want to make a function an argument of a function, which anybody who has done Haskell will probably know already. Mapping functions, right? How many Haskell people in here? And have you used map? A little bit? Yeah.
It exists in Python too, though.
Just in Python?
No, it's in Python too, though.
It is in Python. Yeah. We're gonna explain it. So what a map does is it takes a data structure and applies a function to each element of it, right? So in theory, or not in theory, in practice, if I defined a quick map function here, which takes a function f and a data structure L, for x in L, x is equal to f at x. Very simple, right? So because Python uses dynamic typing, you don't actually know that this is a, like if you just ignored the body of the function, you wouldn't necessarily know that f is a function. But because it's being used like a function down here, that sort of constrains it to be a function as considered by the interpreter when it hits that. Before that, it's like, it's got a, oh, what do they call that? Polymorphic type, technically speaking. But, you know, you won't hear you may not hear the term polymorphic typing until you take 3MI3 with me if I'm still teaching it in a couple of years, and you'll only hear it at the end of the course. And we won't actually cover it because it's advanced type theory. But anyway, so another cool and nifty little trick that you have in Python is anonymous functions. So these are all also known as lambdas. They're called lambdas because of a branch of mathematics called Lamina Calculus, which was developed by a computer scientist by the name of Alonzo Church, who was the supervisor for Alan Turing's doctoral thesis, and one of the two components of the Church-Turing thesis, which of course is a very important result in the early theory of computation. But Lamina Calculus is essentially a function extraction operator. So if you have some expression, right? Let's say you have like x squared plus 3x plus 7, right? Some generic function. Lambda x, x squared plus 3x plus 7, is a function with x as an argument. So it's a way of taking expressions and producing functions out of them, right? So you could, you know, then apply an argument of 7 to that, and 7 would be substituted for each of these x's, and the lambda would be thrown out, and that would be the result, right? Lambda calculus is actually like a, it's a fascinating mathematics because, fascinating mathematics? Anyway. Anything that can be computed in lambda calculus. And by showing you this, I've actually shown you all of the rules of pure lambda calculus. It's really, really quite cool. You guys mind if I do like a 5-minute digression on lambda calculus?
Please do it.
Please? Okay. Are we at like that point in the lecture? I can basically talk about anything I want on my own volition? Okay, awesome. So, you can do Booleans in lambda calculus, right? So, I'm going to have to remember this from my brain, but if you have lambda f, lambda t, that's equal to true. And if you have lambda f, lambda t, f, I might have these mixed up actually. Yeah, I think it's true then false. Because true should come before false, right? Anyway. True and false. False is equal to false. Right? So, essentially, the way that you define Boolean truth values in lambda calculus is as a function which takes two arguments and throws out the second. And then you have false is a Boolean, false is a lambda function which accepts two arguments and keeps the second and throws out the first. And like there are various cool, like this is cool because it actually works, right? oh, I'm trying to remember the, if you take, oh God, come on. Gotta remember this. If you take true and lambda false, or I think it's like, let's just call them n and m, and you apply those to the expression true n m. I think that's how you do Boolean and, but you can do that out. It's so let's say you applied true and true to it, right? Let's just call it t for sake of brevity. So t gets applied to the lambda, which gets put in here, right? So it's t, right? M, you take the t and the second t, you apply it to m, it gets substituted here. So essentially, that expression simplifies to true, right? This true expands to lambda t, lambda f t with t and t applied. So you apply these two things. It takes the first one, which is t, and then so the result of true and true is true. And I can't remember though if this is and or, so let me just run this with false and see what I get. So false and true, applying false. So that would be false, which means that you get that as a result. Yeah, so that looks like it's and. Let me just run it the other way now. So true and false. Aha! Do we run into a pickle? I think we might. Aha! Because that would still take true, which is incorrect. I think it's the other way. I think it's like NTM. I think that makes more sense. So true, false would be true. Yeah, I think that's or. At any rate, I should have studied this. I should have refreshed my memory on this before I launched on this absurd diatribe. But at any rate, you can get the Booleans to work in this stuff, right? You know, actually, once you've got and not, you can construct all of the other Boolean operators from just those two. There's also a way of doing what's called piano arithmetic. So one way that you can define arithmetic inside of like a set theory environment is if you define a system of numbers in which you've got 0 and a successor function, right? Then you can define all of the natural numbers, right? Because, you know, 3 is just successor of 0, right? So it's easy, it's that type of a system you can do in Lambda Calculus pretty easily. It's lambda s, lambda z, just however many s's you want, and then a z applied, and they're all applied to each other. I think like that. So you apply, like you do the, it's sort of, depending on the type of or style of Lambda Calculus that you're working with, you might have to do the outer applications first or the inner applications, or it might not matter which applications you do first as long as you do all of the applications. But essentially, the crux of the Church-Turing thesis was a demonstration that this stuff can do anything that a Turing machine can do and vice versa, right? And it's actually, that result has been expanded such that any model of computation which has yet been discovered by human beings is Turing equivalent. And that's the idea of Turing equivalency. So that's some pretty advanced stuff. Applications to the design of programming languages. You'll study it in second year if you take more computer science courses. It's very interesting stuff. Any questions? No? Okay. So, let's see. So anonymous functions are lambdas. Essentially, it allows you to construct a function in like one expression in line. It's called anonymous because a name is never assigned to it. It's not because it's a international hacking ring. You can, for example, very quickly, if I were to take my list from earlier and map a lambda over it, so lambda x, I think it uses colon, doesn't it?
Yes.
Yeah, cool. Lambda x, x plus 3, save, execute, L is not defined. Oh yeah, because it's list, there we go. None. Okay, yeah, map does return none.
No, it just you redefine map.
Yeah, I did. Give me a second. It's mutable, so this should work. There we go. Oh, God. Come on. Work with me, computer. Is it because I'm using a for loop?
Yeah, for loops are passed by value.
Yeah. All right.
Yeah, that's what.
Does it work? No? Oh yeah, because X doesn't exist. F or L at I is equal to F at L at I. There we go. Boom. Thank you. Any objections if I end class 2 minutes early? No? All right. Thank you very much for all of your attention. Get out of here. Go home.